Okay, so hello everyone. I'm Petr Muzikant, and as you might have guessed from the title, I will be even more technical than the previous speaker. But bear with me. There are some general outcomes out of this presentation, I believe. So in this presentation, after a brief introduction, I will try to raise my credibility by telling you something about our experience with post-quantum implementation or migration. But then for the engineers themselves, I would like to give a little overview on how to begin, where to begin, and maybe give some engineering obstacles that we have encountered and that would be great to look out for if you are embarking on the journey of PQC migration as well. When one does some research on PQC migration right now, he will most probably encounter documents about the timelines, about the migration challenges, but we feel like those focus on this topic pretty abstractly and reasonably so. Don't get me wrong, they are really great to help you make a decision, the decision whether or not, and if so, when to do the PQC migration. But let's say you decide now or tomorrow or you decide soon to migrate. How do you actually do it? Do you or your engineers, your developers have everything in their disposal to have a smooth experience? So this is what I personally and we have been focusing on engineering aspects of post-quantum migration, where it is right now and what is there for us to fix, basically. And there is a lot of stuff to fix right now. Our experience, we have started with post-quantum proof of concept in several e-government applications that most of you probably know or at least heard of. We have the Web EID, CDOC2, ISIC-E, and IVX3, the authentication, encryption, digital signatures, and e-voting frameworks. In fact, or to be more specific, it was more about implementing post-quantum in underlying and supporting projects other than the e-government application themselves. So we have been dealing with a lot of post-quantum library wrappers, some post-quantum OCSP and TSA solutions, and most recently also having a look at some lattice-based crypto development kit, which should help with future applications based on lattice-based crypto, which is one of the I think free post-quantum crypto families. How do, as an engineer or someone who has a task to migrate to post-quantum cryptography, how do you begin? I guess it's a common or general advice to start with a preparation. So during these, we have found that identifying all objects in the code base in your system that are potentially vulnerable to the quantum computers, that's their identification and most importantly their lifetime in the system. So places where these objects are created, where they are transported, when they are deleted out of computer memory, for example. This is pretty good to know. It helps you to understand the extent of required changes that will be required to do in order to migrate. So I have an example of, for example, digital signature objects in the code base, or key agreements, public keys, certificates, etc. It is also good to note the maximum transmission units when you are transferring these objects between different system components over some networks, because post-quantum objects, as it already have been said from the previous speaker, they have quite much bigger object sizes, so it is good to look out for that, and also the changing data formats, because the change between these formats is not yet seamless, and it requires some thought to be put into that. As an example, we found that making BPMN diagrams is pretty good to denote all the information from previous slide into one picture. So we have an example from WebEID, from the authentication workflow, where in the red color we have denoted all the objects or all the places where we need to implement the post-quantum cryptography. And we have some comments there about the data formats and maximum transmission units. Next, it is good to assess the current boundaries of the system and count with a increased performance, memory, and storage overhead. But this is more targeted towards limited devices and slow networks, since current computers and mobile phone CPUs are pretty sufficient enough for post-quantum cryptography right now. Also, if there are any troubles on the limited devices, don't worry, because there have been already some research done on some protocol adjustments in order to fit them, for example, into limited memory of embedded devices, for example. Okay, and the last step is the implementation itself, which the rest of this presentation will actually be about. I can only recommend to start at the beginning of the data lifecycle that we have denoted few slides before, and implement the post-quantum support step by step. It is very probable that you will have to encounter a lot of adjustments and adaptations that you need to do, because, as I said, the implementation is not yet seamless. So where to begin? I think it is good to do a little overview on the algorithms themselves. The probably most fully followed standardization process is from NIST, from America, the National Institute of Standards and for Standards and Technology. And recently they came with a free official standards that they are looking to standardize this summer. So right now, there we have one algorithm for key encapsulation mechanism, which you might probably know as Kyber. So it is being renamed after some adjustments to MLChem, and also it will. I think it's the third quarter of 2024 where they will announce a winner from another round of key encapsulation mechanisms. But the official standard will come much later, probably. For digital signatures, we have dilithium and Sphinx, MLDSA and SLH-DSA standards, also being standardized this summer, and also Falcon, but there have been some issues with finalizing the technical details, because it is, in order for it to be efficient, you need a floating point arithmetic, which is not easy to do on every device, basically. So the official standard will come up probably later. And also there is another so-called on-ramp standardization effort, but we have so much time to see any standards coming out of that. There is this on-ramp round because the NIST is looking for different crypto families other than lattice-based digital signatures, which the dilithium and Falcon are. And of course, there are other evaluation efforts from different countries, so we will probably expect more algorithms coming out of that. Next, a security engineer will most probably have to look for some cryptography libraries. So I would say that these first two, PQClean and libOQS, OQS means Open Quantum Safe, it is an organization that creates these. These are the two most well-maintained, and I would probably say easy to go to and use. They are most probably the same. They have the same algorithms, but they have different purposes. The first one is only the source of the source code. So the authors of the library encourage you to copy the code and put it into your project and build it yourself. So it is good for example, the IoT devices, for example. The libOQS itself is much higher library, so it can be used in higher level applications. and it has also a lot of wrappers for different programming languages, so it is really easy to use. In case you need something else, there are of course providers, crypto providers that are programming language specific or platform specific, so it might be a good idea to research those as well. Okay, we have already heard something about algorithm identifiers. I will kindly leave this slide for a little bit later because it fits more into the next chapter, which are the engineering obstacles. So we already can see here that algorithm identifiers are really problematic right now. And I will talk about it later. Object encoding, this is also something good to know, that the NIST submission rules listed that the people who created these algorithms should implement those such as it should take input and output only as raw bytes. And however the object or the, let's say, digital signature is encoded in those raw bytes, it's up to the NIST submitters themselves. And as far as you are using the official API, which the liboqs and pqclean are using, then you should be fine. When you just have to ensure that the output from one, let's say, system components travels successfully to another system components, and you shouldn't have any compatibility issues. But today, I guess the most crypto applications are using the ASN1 structures or ASN1 encoded objects. So there have been already some efforts to increase the interoperability between different crypto providers. And the IATF hackathon group, which I believe was not mentioned in the previous presentation, in the first couple of the slides, is actually trying to come up with, or is trying to persuade crypto providers to settle in at one specific ASN1 structure for specific algorithm, for example. But we can already encounter these being used in different crypto libraries. For the most notably, the bouncy castle doesn't actually allow you to input raw byte. You have to decode it into or encode it into ASN1 structure yourself, which is quite problematic, and I will talk about it in a little bit, I believe. Also, the hybrid mode, which was already also mentioned, it is a combination of post-quantum cryptography and classical cryptography, so you get the best of the both worlds at the cost of a little bit increased in performance overhead. So the post-quantum cryptography ensures the longevity of data protection, while the classical cryptography protects us against some emerging threats on unexplored PQC. And I believe these unexplored threats will be a topic in one of the following presentations. Also, the most common modes today, I would say, are concatenation or sequential modes, where in concatenation you put the, let's say, post-quantum cryptography digital signature and classical digital signature together, or in sequential you use one output as an input into another. So a post-quantum cryptography digital signature gets inputted into, gets signed by classical cryptography, or vice versa. However, the concatenation mode is more famous right now. So we have heard that Cloudflare and Google are using the already mentioned combination, so it is concatenating the two together right now. So the engineering obstacles. So in other words, the stuff to watch out for or look out for when you or your engineers are doing the PQC migration. The general outcome is that the PQC implementation is far from straightforward right now. There are a lot of obstacles, but they need to be talked about in order to increase the smoothness of the experience in the future. So algorithms identifiers, it is the same slide as before, but I have now expanded it because especially with ASN1 object identifiers, unfortunately, it feels like a Wild West right now. There are multiple organizations trying to come up with their own lists of object identifiers, and these lists are not 100% consistent with each other. Also, the introduction of, or the renaming of MLChem from Crystal Kyber to MLChem has also increased the confusion, because in MLChem, the specification in the official standard, there is one chapter which is called Differences from Crystal Kyber, and there are some technical details on different technical decisions. So, at least to my understanding, these two algorithms should have different object identifiers. The MLChem came out of Kyber, but they are different algorithms on the technical level. But yet these two has already been confused between one another in those sources of object identifiers. In case your application requires different algorithm identifiers, like JSON web algorithms or XML signature syntax algorithms, which are still being used, I have to say, unfortunately, that it is probably a better idea to create your own temporarily in your testing scenario or in a proof of concept, because looking or searching for those is a long track, long and confusing track. So in our case, we have been temporarily creating our own identifiers. Also, the object encoding, a lot of crypto libraries that are being used today have these classical algorithms hard-coded in them, so it is not really possible to just plug in something and have a post-quantum cryptography out of the box. So preferably, what we are trying to do is to extend these libraries. If they are open source, then we try to introduce the post-quantum cryptography there and publish a pull request on GitHub or something to help the community with these. But I understand that there might not be much resources for that. So what you can do is to go around the problem and introduce some splitting in the code flow, basically, where in case your system encounters the classical cryptography, it is using the classical library. In case it encounters the post-quantum cryptography object, it splits into a different if statement where you are using only the lib OQS, for example, which is the pure PQ library. The last two slides actually basically create another issue, and that's interoperability issue. As an engineer, you have to very actively think about what happens if you choose an algorithm identifier, but your system is communicating with different third-party system, and authors on the other side have decided to use a different source of algorithm identifiers. If your system is outputting digital signatures in raw bytes, but then you need to transfer those raw bytes into a component that's using bouncy castle, and then you need to encode it into the ASN1 structure in order for bouncy castle to be able to operate on that. So I guess this general question of if I introduce a change into a one part of the system, does it break all the other parts of the system? This is pretty a common question in engineers' workflow, but my point here is that with post-quantum cryptography, the issues that these questions raise are much more magnified at this moment, and you have to do even more active thinking about all this. Also, something about the cryptographic tokens, because in most of the e-government applications, the smart cards are currently used, but currently it seems like there is not any available smart card that is capable of doing post-quantum cryptography. So for a local and testing purposes, we have used a programmable embedded devices. Since their performance and memory capabilities are quite okay for post-quantum cryptography, however, we understand that it is nowhere near usable in the real-world application right now. So we will have to wait for chip manufacturers to actually come up with some PQ-capable smart cards. one of the last things for this presentation, the maturity of post-quantum crypto. We have seen that digital signatures and key encapsulation mechanisms are the ones being standardized, and it seems that the multi-party computation and homomorphic encryption will follow this standardization process, or at least the standardization bodies and the community is thinking about them. But what happens if your application requires some special features? For example, in the e-voting, we are currently using ElGamal in vote encryption because it has a special feature of decrypting the ciphertext in case you are the one who did the encryption, because you are the holder of encryption randomness. This is really something that we haven't seen and we will probably not see in the post-quantum cryptography any soon. So in these cases, I guess the internal research and development needs to be done, or you will have to wait for some research efforts from abroad. Some miscellaneous PQ engineering efforts. I won't go over them into details. You can ask me about them later if you want. My point here is that my list of engineering obstacles was not complete, and there are many more. I called it all the little things. They were not hard to solve, but they are there. So that's the message here. And to jump to the conclusions, I would say that implementing post-quantum cryptography today is complicated. It is not straightforward, but it is doable. I would say it is worth it because you are introducing the needed long-term data protection. You gain a lot of experience, and I think one good outcome out of PQC migration, apart from creating a quantum-safe solutions, is that we have a rare opportunity to create or set good practices in the cryptographic world. So we have a chance to rethink all of what we are doing in the cryptography world and possibly make it better. And lastly, it is helpful. There is a big space for open source PQ contributions. And it is probably needed to reduce the confusion that I have been talking about. So a collective resolution or collective engineering resolution is really welcomed here. Okay, that's it from my side. I thank you for listening, and that's it.
Thank you very much. So, to follow up for the question, to a question we had for the last talk, hardware. Chips, pin, SIM cards, chip cards. How far are we? Can this be done? Should this be done?
Honestly, I think nobody knows, because it seems like the chip manufacturers are not that open with information on how the migration is doing. Mm-hmm. And I guess if somebody is looking out for those embedded devices, maybe there will be a better ways to maybe they will come up some better hardware solutions that will be capable of doing PQ crypto, but at the same time will be easy to certify, for example.
Coming to certification, enterprise HSMs, are there any that have PQC or rumors of any?
Not that I'm aware of, I guess.
Likely too early. Questions from the audience, please. Yes.
So am I correct, as I understand, the whole logic is to find a better mathematical problem and then use it for creating algorithm. So my question is, this new post-quantum algorithm can be converted into for classical devices later on. So we just found a better algorithm, which is more protected.
Yeah.
Yes.
Yeah.
No, you.
So if I understood the question, is that if you're asking if the PQ is capable of running on classical devices? Yeah. Apart from the smart cards, I would say yes. It is doable. If you have an application that is running on a computer, it is a question of exchanging one cryptographic library to another. So the post-quantum cryptography is actually a software. It's a software-based solution. If you have opportunity to change the software, the code, then you are able to run the PQC there. I hope I understand. I answered the question.
I think that was a good point, which we didn't make earlier today. Post-quantum cryptography is a software upgrade. It's no new hardware upgrade unless you are running on very constrained hardware.
Which are smart cards, for
Yes.
example.
One more question, yes?
Hi, hello. Thank you for the presentation. Actually, I'm connecting to this, so coming back to the hardware. You had a slide, so can you say anything related, for example, to the usage of FPGA for implementing? So I think you have a board, but probably you do software implementation with an ESP32, but...
I hope I can refer you to actually another presentation today, which will be about the hybrid cryptography by Jan Heine. He will probably talk about usage of PQC on FPGAs in more detail.
Thank you.
Yes, but this is, many people are doing this.
Mm-hmm.
People are trying to build PQC accelerators on FPGAs, and they are thinking about ASICs already, because that's where it has to end up one day.
I would say there are a lot of startups also with these kind of applications.
Yes. One more question?
Regarding implementation vulnerabilities and risks connected to it, my question is twofold, one for primitives and one for protocols. It seems to me that everybody is using Open Quantum Safe library regarding the primitives. Are there even other sources of implementations? And do you think that the using just one library is a good thing or a bad thing for the risks? And the connected questions to the protocols.
Yeah, well, I would say that in this era where the engineering or interoperability stuff is not finalized, there are also a lot of IETF RFC drafts being used that are already expired, as was your last question. So in here there is a common ground with those. I would say that for its era, it's good to have one library that works because at this moment you are not really building a PQ implementation or PQ application. You are building the proof of concept, and you are trying to see if it will run on all of your devices. So I would say for this moment it is good to have one library that is reliable and it works. It's being updated regularly by multiple people from multiple organizations. So that's that. And for the applications themselves, I guess you are referring to another applications from the libOQS, from the Open Quantum Safe, which is not only doing the library itself, it's also building the OpenSSL and OpenSSH forks built on top of libOQS. So I honestly don't know if only the Open Quantum Safe solutions will be used in the future. But for this moment, they are the most mature enough, and using others that are either not updated regularly or they have they are using the expired RFC drafts. It's a recipe for problems, engineering problems right now, unfortunately.
If there's one short question, we still have time. The speakers have been great on time. Excellent. Thank you very much, Petr. This was great.
Thank you.